Hello everyone, my name is Guillermo López-García and I work as a PhD student at the ICB lab, the Computational Intelligence and Biomedicine Research Group at the University of Malaga, Spain. So I'm here to present our contribution to the CLEF eHealth 2020 Task 1. Specifically, we have exclusively participated in the CodiEsp diagnosis subtask. So at the beginning, when facing the challenge, we decided to develop a fully machine learning based approach. For this purpose, we used BERT language model. In this way, we treated the CodiEsp D task as a multi-label text classification problem, and we used an output classification layer of multiple sigmoid units on top of the C token representation generated by BERT. The main issue we encountered was that BERT can only process a sequence of subtokens with a maximum size n, with n equals 512. However, most of the clinical cases present in the CodiEsp corpus have a subtoken sequence size clearly above the maximum length supported by BERT. To overcome this limitation, we developed a three-phases custom strategy, which I'm going to illustrate next, using a clinical case extracted from the CodiEsp corpus as an example. So firstly, we split the document into short text fragments compatible with BERT. Then, during the second phase of our approach, in order to annotate each produced fragment, we used the information available for the CodiEsp explainability subtask. In this subtask, code's annotations include an extra field indicating the reference in the text that explains the coding assignment. In this way, using the previous information, we managed to annotate each fragment exclusively with the ICD codes whose text references were contained within the limits of the fragment. Using the annotated short fragments of text, the BERT model was trained on a multi-label fragment classification task. Hence, at prediction time, given a text fragment as input data, the model produces the probability of each code to be present within the input fragment. However, CodiEsp D task is a document classification problem, and the evaluation of the participating systems was performed at document level. For this reason, the last step of our three stages custom strategy consisted in applying a maximum probability criterion to obtain the code's probabilities at document level. In this way, for each predicted code, we simply selected the maximum probability predicted by the model across all fragments in a single document. Finally, when submitting our results, we must say that in order to optimize the mean average position metric, for each document we returned a list of all codes sorted in descending order according to their probability values predicted by the model. To conclude, we now summarize the results obtained by our team in the CodiEsp D subtask. So we submitted three different ranks of our system. The first two ranks correspond to the BERT Cielo model, and the third rank corresponds to the Beto model. Both models are based on the BERT base architecture, pre-trained from scratch on a Spanish corpora. However, while Beto was pre-trained on general domain text, BERT Cielo was pre-trained on a corpus of biomedical articles. As we can see, considering the mean average position official evaluation metric of the task, BERT Cielo clearly outperforms better, achieving our best score of 0.482. So that's all. Thank you very much for your attention.